Hi, I'm Laurie Bose, presenting the paper Descriptor in Pixel, Point Feature Tracking for Pixel Processor Arrays. As a forewarning, there are no neural networks involved in this work. So first, a quick reminder, what are point features? Well, point features are small, distinct visual features that are tracked across frames. In a traditional approach, we first detect key points by performing something like blob or corner detection. Then for each one of these key points, we build a descriptor, which is a compact representation of the point's local image. And then tracking is performed by matching the descriptors of these key points across frames. These point features are used to deduce the motion of the sensor or other objects, and are used throughout computer vision, playing an essential role in SLAM, visual odometry, augmented reality, VR, any application where you need to track the motion of something essentially. Okay, but in point feature detection and tracking, how much of the image is actually useful? How much of it is used to contribute towards the detection and tracking of these features? Well, it's only a tiny percent of the pixel data, say around 1%. So what happens to this other 99% of the image data? Well, essentially nothing. It's discarded every frame, thrown into the trash. So we have this extreme inefficiency here. We're transferring whole images from sensor to processor, but most of this data is not useful at all for our task, and this is true for many real-time computer vision applications. So how did we get to this situation? Well, cameras have been around a lot longer than computer vision, and are primarily designed to capture pictures for humans to analyze, not for efficient computer vision. But this process of whole image transfer has many significant costs. For one, it's extremely slow in terms of electronics, introducing latency and limiting the rate that algorithms can effectively be run at. It's also extremely power hungry, and there are major privacy concerns in a world where you have hundreds of internet-connected devices streaming camera images. So how do we avoid image transfer? We really need to fundamentally change the hardware, and one option is to move computation directly into the pixels of the sensor itself. This is the concept of the pixel processor array, a sensor in which you essentially have thousands of programmable pixel processors, each connected to their immediate neighbors, and this allows you to perform computer vision in pixel, as it were, and extract high-level information. Then, instead of outputting whole images, we can output just this high-level information. In this work, we make use of the SCAMP pixel processor array, a prototype created by the University of Manchester. It has an image resolution of 256 by 256 grayscale, which may not sound like much, but it's still 65,000 pixel processors. Interestingly, it is also mixed signal, meaning it's analog and digital computation. It operates as a single instruction multiple data computer, which means each processor executes the same program in parallel, but they are all operating upon their own local data, similar to GPU compute. As you might expect, the resources available to each individual pixel processor are very limited. So in SCAMP-7, the pixel processors have analog and digital memory and can perform operations on both of these. So in terms of digital memory, there is 20 bits of memory per pixel processor, and you can perform basic Boolean logic between these bits of memory. In terms of analog memory, there are 7 memory registers in which continuous values can be stored, and you can perform operations between these registers, such as addition, subtraction, divide by 2, or thresholding of an analog result to a digital register result. Here we see the traditional pipeline for point features, whereby a standard camera captures an image, and then this image is transferred from the sensor to CPU and GPU, upon which point feature detection and tracking is then performed. How are we going to change this pipeline? Well, first, of course, we will replace the camera with a pixel processor array. This then allows us to move the computation required to detect and track these point features directly onto the sensor. Now the sensor can output the locations and descriptors of these features directly, rather than whole images. This is a massive reduction in the amount of data transferred from sensor to processor per frame, and will give us huge improvements in efficiency and power usage, allowing us to run at thousands of FPS at only 1 watt of power. Now turning to the actual algorithm being performed upon the pixel processors, the first question to ask is how to divide computation between them to perform detection and tracking of point features. Well, let's say we have a point feature located inside this processor here. a natural thing to do would be use all the surrounding processes to track that feature. And we can do the same for all other point features. All point features are tracked using their surrounding pixel processes. Any remaining pixel processes can then be used to try and detect new features. So in summary, processes near existing features are used to track those features, and processes not near any existing features are used to detect new features. So we have these two different tasks being performed upon our pixel processes. But how can we perform these two different tasks in parallel when the pixel processes operate in SIMD, all performing the same program? Well, the answer is we need to perform both detection and tracking using the same computation. This is where we introduce the idea of descriptor response, which is a mechanism for performing both detection and tracking in parallel. It involves storing a small descriptor inside every pixel processor, where this descriptor encodes some specific kind of pattern or image structure. Then, in parallel, every pixel processor can determine how well the structure encoded by its descriptor matches the local image content. We call the measurement of this descriptor response. Here we see an example where on the left we see the captured image, and on the right we see the descriptor response within all pixel processors. But what is this response actually doing? It's highlighting image structures which match the descriptor stored within the pixel processors. And within this response map, there may exist well-defined local maxima, such as at the cross of the 4 highlighted here. We can pull out these well-defined local maxima by first performing blob detection, and then thresholding upon these blob detection results, pulling out the most reliable local maxima. And what these local maxima really are point features that exist within the response of that specific descriptor. And detection and tracking of point features then comes down to essentially finding and following these local maxima within the descriptor response. In the previous examples, we've just used one descriptor, but of course, different descriptors will produce different responses highlighting different image structures. And if we perform blob detection upon these responses, and then perform thresholding, we can see there are a different set of point features existing within the responses of these different descriptors. And of course, we don't want to just detect and track features from a single descriptor. We want to track features of many different descriptors all in parallel. So how can this be done? Well, the first thing to realize is that at very high speeds, the positions of local maxima, i.e. point features, will barely change from frame to frame. This means to track these features, only a small amount of descriptor response around each feature's location using its descriptor is needed. And the other thing is, of course, we don't need to store the same descriptor inside every pixel processor. Every pixel processor can store different descriptor in its own local memory. In this simple example, we've loaded the pixel processors in one half the array with descriptor 1 and the other half the array with descriptor 2. Then when we compute a response, we can see each half the array is essentially highlighting a different type of image structure. So if we have a number of different descriptors, each containing a different set of point features, to perform tracking of these features, it is not necessary to store the descriptors across the entire pixel processor array. We only need to compute a response of their descriptors around their locations for tracking, and therefore we only need to store the descriptors around the pixel processors of those features. All of these different patches of descriptor response for the various features can be fit onto the pixel processor array simultaneously. This allows us to compute the responses needed to track all of these features in parallel. And then into all the other pixel processors which are not being used to track any particular feature, a random search descriptor can be loaded, the response of which may contain new features. So here's all this running on SCAMP. You can see the images on the left and the response computed on the right. You can see this flickering, which is the random search descriptor which is changed every frame. Any local maxima occurring within this descriptor are initialized as new features. And you can see the patches of various descriptor responses around each feature. Each feature then just simply follows the local maxima of its response every frame. Here we see another example in which we've strapped a SCAMP and a cell phone together. We are limited here to 1000 frames per second because we are outputting a 1-bit image every frame and then stacking these 1-bit images to form a 4-bit image in order to visualize what's going on within SCAMP. However, this output is purely for visualization. We can still see that under rapid motion, we are able to track point features reliably because they barely move from frame to frame at 1000 frames per second. By comparison, the smartphone's image is often rendered pretty unusable due to motion blur. But again, this image transfer is purely for visualization. In a real application, the SCAMP sensor can just directly output the feature locations and descriptors. This reduces the data transfer per frame to just 16 bits per feature, which allows us to then reach 3000 frames per second. As a summary of how our approach differs from the traditional camera-based pipeline, rather than detection tracking being two separate disjoint processes, everything is handled by descriptor response, essentially just finding and following local maxima within the descriptor response and then updating the locations of descriptors within the pixel processor array based on this response. Also, it is fundamentally different in that the traditional approach has complex and sparse descriptors, using very long descriptors but only at the locations of sparse key points, while our approach is simple and dense in that it has simple, in this case 8-bit descriptors, but placed at all pixel locations simultaneously. So to conclude, we present the first work where point feature detection tracking is performed entirely in pixel, by which I mean all computation necessary is performed upon the pixel processors of the sensor itself. Descriptor response is also introduced as a mechanism by which detection tracking can be performed entirely in parallel. Our system does not need to output any images because all computation is performed upon the sensor. Instead, we can just directly output the feature locations and descriptors. All this adds up to 3000 frames per second performance using 1 watt of power. But it is also important to remember SCAMP is an academic prototype, manufactured in 180 nanometer, which was cutting edge technology back in 1999. And if a sensor was manufactured using modern techniques, you might have some truly amazing applications.